So we're here for a second example using base E and LN, and it's another half-life example, but this time it's actually, instead of plutonium, we're going to be looking at carbon-14 in a fossil. Not this fossil, but a woolly mammoth. So let's go ahead and look at an example. So let's see, this will be example 2, right? So let's say a specimen originally contained 42 milligrams of carbon-14. And now has 8 milligrams. So we want to know how old is the fossil. Okay, so one of the things that we're going to need to know that I haven't told you yet is we got to know the decay rate for carbon-14. And again, it's an unstable isotope, but it decays in a predictable manner. And so the decay rate for carbon-14, so we'll say the carbon-14 K value or decay constant is, let's see, negative 0.00012, right? And actually, well, yes, it's 0.00012. It's negative, making it decay. So let's think, first of all, let's figure out what we know. So that's that question. What do we know? So look in the problem. What are we given? 42 milligrams. And it says that's how much it originally contained. So think about, in our equation, F of t equals A times E to the negative KT. Who is 42? Yeah, it's A. So we know that A is 42 milligrams. And what else do we know? Well, who's this? It now has 8 milligrams, so that is F of t. That's an amount after some time t. So we know F of t. And because we're talking about carbon-14, we know the K value, right? We know that K, or negative K, is negative 0.00012. So we know A and F of t and K. E, remember, is the letter, but it's not a variable, of course. It's Euler's constant. So what's the only thing in this whole piece that we don't know? Well, we don't know T. Is that what they're asking us to find? How old is the fossil? Yep, that's what we're asking to find. So we can figure this out. Let's plug in everybody that we know into our equation. So we're going to say 8 equals A, that's 42, times E to the negative K, so negative 0.00012 times T. Let me write it that way. Negative K equals negative, right? So now we're going to work backwards. And so when the variable is in the exponent spot, you know that at some point we're going to have to put it in log form. But before we put it in log form, we've got to isolate the exponent, e to the whatever. So if we have anything that's being added or subtracted, we need to undo that. If we have anything that's being multiplied or divided, we need to undo that. We got this 42 out front. Let's divide both sides by 42. And now we have 8 over 42. Just leave it. equals e to the negative 0.00012 t. And now we're at the wall. E to the stuff equals number. So we can't go any further, but look where the variable is. So we got to logify, right? And oops, that's supposed to be a t. We got to logify. So now we're going to say the natural log of 8 over 42 equals the exponent, which is negative 0.00012 t. And to solve this for t, we undo the multiplication. So we're going to divide both sides by negative 0.00012, divide by negative 0.00012. And really, I know part of you is like, this bothers you that I'm not simplifying 8 over 42. Really, no intermediate rounding, because 8 over 42 is not a friendly number. So just leave it. Just leave it, okay? And we don't round until the very end. So now it's calculator time. So just get out your calculator and just say the natural log of 8 divided by 42 and close the parentheses, just like that, okay? And then what? You can hit enter if you want, and you got that big old long irrational number. And now you're going to say divided by negative 0.00012. Look at there. So let's write our answer down and then see if it makes sense. So this pen, everybody's using the internet at once and my pen does not want to respond. T equals 13,818.567. So we'll say 57. All right, now let's go back and see if this even makes sense. And we rounded, so let's put in approximates. The question is, how old is the fossil? Does this make sense for the answer of the age of a fossil? I know this isn't a mammoth bone, but okay. Does it? Well, sure. Could you have a fossil that was 13,000 years old? Yeah, you could. So let's write our sentence, because we always need to answer a word problem in a sentence. And the question is, how old is a fossil? So we could say the fossil is about 13,800, and we'll round to the nearest year. How about that? 19 years old. Okay. All right. If you need to press pause here, go ahead. I'm going to work a second piece to this, but this lets you know how we can use carbon-14 and exponential decay and logarithms to figure out the age of old stuff. Okay. All right. Our second example in this same, well, it's the same example, but a second piece. Now we're going to look at like a woolly mammoth specimen, okay? Slightly different. So most of you probably have thought about or seen, it's just like a hairy elephant, but much larger. A woolly mammoth specimen. So we've got a bone or tusk or something. And let's say that it is, we think we know the time on that. So we'll say it's thought to be about 12,000 years old, let's say. And that's about right, I think, for what, when they think most like saber-toothed tigers and woolly mammoths were here. All right. So now we want to say if, because again, paleontologists do this, if I think it's 12,000 years old, then it should have a certain amount of carbon-14. All life, all things that were living that had carbon in them are going to have a certain percentage of carbon-14 if they're 12,000 years old. That's what's so cool about it. It's predictable. That's math. Okay. Nifty. Okay. So here we go. We're going to say how much carbon-14 should be in the animal. So is it really a 12,000-year-old woolly mammoth tusk, or is it a hoax, right? How could you find out? Well, you could do carbon-14 dating and some log stuff and figure it out. All right, so here's the question. What do we know? Let's write down all the stuff that we know. Do we know the original amount? No, we don't. Okay, so remember from the earlier example, if we don't know the original amount, how much was there? All of it, right? All of it, 100% or 1. Okay, and we know E. Do we know K? Well, it doesn't tell us K, but it tells us carbon-14. And in the example that we just worked, we found out what the decay constant was for carbon-14, and it is this. K equals, it is 0.00012, but because it's a decay, right, it's going to be negative K, so it's going to be negative 0.0012. Do we know T? We do, 12,000 years. Do we know F of T? No, that's what we're trying to find. How much should be there? So after 12,000 years, how much carbon-14 is there? We don't know, but we can find out pretty quick. So let's put everybody in the right position into the problem. So we're going to come right over here. F of T, we don't know, equals A, 1, times E, E, to the negative K, negative 0.00012 times T, which is 12,000. That's a pretty big, cumbersome exponent. Now, this is a sweet problem because if you look, where's the variable? It's over on the left. Where's all the numbers? Over on the right. So we don't have any backward solving or anything. This is straight up, put that sucker in your calculator and push enter. And that's what we're going to do. So we don't have to put in the 1 times. Okay, we got that. So we're going to say E, so second, ln. So now I'm going to say to the negative 0.00012. And then while I'm still in exponent, I'm going to say times 12,000. So it's going to look like this. Can you see? I know it's a glare. Can everybody see? Okay. Now I'm going to push enter. And here's what I get. So when I write that down, F of T is my amount after time T. What did I get? F of T is approximately 0.2369. What does that mean? Well, let's make that a percent. If I started with 1, I have now 0.2369, which is about 23.7%. So however much I had at the beginning, after 12,000 years, I got, what, about a quarter of it left. Yeah, about 23.7%. So we can make a nice little sentence and say, there should be about 23.7% of the original, original, the original carbon-14 left after 12,000. 10, oh my stars, years. Wow. Isn't that cool? So science people are going to be like, this is science, it's so cool. It is cool though, all right? So that is our second example of decay. The next few examples we're going to look at are going to be exponential growth.